Hello everyone, thanks for joining me. I want to talk about building a gravity simulator and using something called object-oriented programming to help us out a lot. So I will start with a gentle introduction to object-oriented programming. That'll allow me to pronounce it a little bit better as well. And the system that I want us to work with is the moons of Jupiter. So if you would like to take what we produce at the end of this and look at, say, a galaxy simulator or a solar system simulation, that's really cool. I like starting with a simple example where the bodies are relatively close together and where in a reasonable amount of time we'll actually see some orbits happen without needing to wait around a while for our simulation to finish. And so I'm going to look at the first moons that were discovered other than our own moon, which were discovered in the early 17th century by two people, Galileo being one of those. And Jupiter, in fact, has the most moons, or it did until recently when Saturn overtook it. But the first ones that were discovered, other than our own, were Ganymede, Io, Europa, and Callisto, these 4 moons of Jupiter. And so it's a cool system to look at from that historical perspective, too. I want to think about this as a computational problem, though. So what might be the input? What might be the output? And our input here might be an initial configuration of a universe of bodies, the number of generations that we want to simulate the system for, and maybe some decimal number time. And that time is going to tell me the interval. So after how much time should I update the system? If I take a very small value of time, then what's going to happen is that I'm going to get a very accurate estimation, but I might have to run my algorithm for a really long time. If I take a big time interval, then I'm going to get a lot of round off, although I'm going to get a faster simulation for the same amount of total time. So that shows how with a lot of parameters like this in practice you get this trade-off between accuracy and speed, and we'll see that when we simulate this and program it ourselves. In the meantime, I'll point out what's the output. Well, it's all the configurations of the universe. So just as we looked at generations of a cellular automaton, we're going to have all the configurations of the universe, starting with the initial one, and then this configuration is approximated every time, say, seconds, all right, whatever unit of time we pick. Of course, we might say, well, we have all these bodies. They could be moons or stars or planets or so on, but what type should these bodies have? We're familiar with working with arrays or strings, integers, these types of typically built-in types. And we need to make some abstractions here. And so I'll have you recall that when we worked with cellular automata, we thought of these as a game board. Behind the scenes, we thought of them as a 2D array or slice of booleans or integers, as the case was, whether we were working with a 2-state system where it made sense to use booleans, or a k-state system where we needed to generalize the type of each cell to an integer. But I also thought about this system as just a game board, all right? And so that helped me think of it as an object in and of itself, so that, for example, when I was thinking of a number of generations, I could think of it as just an array of game boards. And so the power of abstraction is going to be important. So we want to abstract what is it that's contained in, say, a body? What is it that's important about the body in order to produce a gravity simulation? I'll take a step back from that and ask a simpler question, which is, imagine that we're drawing figures on a canvas, which is something that we had kind of already seen a little bit of with respect to cellular automaton, where we need to draw cells and fill in the cells with colors and so on. But say we're producing something like this, or something like PowerPoint or OmniGraffle, where we have shapes on a screen. And what might be the smallest amount of information for the computer to represent, say, a rectangle or a circle in 2-dimensional space? So with these exercises, I'll have ask you, if you like, you can think about this and pause the video. Otherwise, I'll continue on. In the meantime, often students will tell me, well, a rectangle really can be represented by a corner point, and that corner point might have coordinates, say x1 and y1. And I might think of the corner as, say, the lower left corner. I could use upper left or upper right or whatever I like, but I have the x and y values of that corner point. And then I need a width and a height. So all of these are going to be decimals. So I'll have a width and a height, which are presumably floats. And I'm going to conceptualize this rectangle then as an object that contains these four attributes: the x and y coordinates of its corner, as well as its width and its height. And these four attributes are going to be called fields. So I've provided a generic language-independent way of writing out what are the fields of an object. I'm going to declare an object type. So I'm thinking about a rectangle object, and it has these four fields. And if I want to access the fields, then I will use a dot. So if I have a rectangle variable, I will use a dot following the variable name, and then access the appropriate field. So if rect is the name of a rectangle, then I can get that x coordinate with rect.x1, and say I want to update it to equal 3 times, the y coordinate rect.y1, and then subtract 2. That would be the way that I would access these typically in practice. We'll also be able to, we can declare rectangles, we can change their fields, we can produce them as output of functions, we can pass them into functions. And so I could pass a rectangle object into, say, an area function, where we compute the area of a rectangle. And it goes to show you that we don't need to store this area as a field of the rectangle object. If I know the width and height of a rectangle, I can simply take their product, rect.width and rect.height, and return that as the area of the rectangle. If we look at a circle object, then it may have different attributes or fields. Some of them may be shared. So in this case, we wouldn't be looking for a corner point, but we would have an anchor point of the circle, which is the center of the circle. And now the radius will determine kind of how, what are the points a given length away from this center point, and that's going to form the circle. So the circle in this sense is defined by the center point in terms of its x and y coordinate, and the radius of the circle as well. So all well and good. Here are two simple shape object types. You may, though, have noticed, well, this isn't a perfect rectangle type because the circle won't change when I rotate it, but a rectangle will. And I can only represent an upright rectangle currently. And so you might pause to think for a second about how we might represent an arbitrary rectangle in two-dimensional space. So how if the rectangle is kind of slanted or something, rotated slightly, how would I represent that arbitrary rectangle? In the meantime, I'll continue and point out that students will have two answers for me often when I ask them. One answer would be to add a fifth parameter here, so a fifth field called rotation. That maybe could range from, if we're measuring it in radians, 0 up to 2 pi, maybe not including 2 pi, but that would allow a 360-degree rotation of that rectangle. And so that would allow the rectangle to rotate. So we have a corner point, a width, and a height, and now it's got a rotation to it as well. Another example that students will give me would be to say, well, why don't I just think of the rectangle as 4 points? Maybe this representation of the rectangle isn't so great, so I'll think of it as just 4 points, and maybe I could create a point or an ordered pair object that has an x and a y. And so the rectangle would have 4 of these ordered pair objects, and so I could think about, an object could have another object type as a field. So here the rectangle has 4 fields, which are 4 ordered pairs, and each of those has an x and a y field. And that's fine. That's a great way of setting this up. We'd have 4 points, and then each has an x and a y. Is there one that you might prefer? Is there one that you think is better to work with, or easier to work with, or maybe even superior? Turns out there is. So idea 2 has a flaw. And that flaw is that I could put 4 points in the plane and break this rectangle. There is no rectangle that can be formed from these 4 points. And if I tried to join them in the natural way to form a quadrilateral, I would be claiming that something is a rectangle that isn't a rectangle. And so idea 2 has this problem where we can give it certain values where it doesn't represent the object that it is claiming to represent. It might be a good representation for a quadrilateral, but not for a rectangle. even with a quadrilateral, the 4 points could all be in a line, and then what would we do? Okay, so there's a great quote here on abstraction and the power of abstraction, but what abstraction really means, from Grady Booch, who is a famous software engineer. And he's pointed out that what an abstraction does is denote an object's essential characteristic that distinguish it from another type of object and allow us to have very crisply defined conceptual boundaries. The critical part of the quote being that it's relative to the perspective of the viewer. So when we, for example, pass in 5 fields to a programming language and say that a rectangle contains these 5 attributes, we're the ones who are thinking of this as truly representing a rectangle. And we're the ones who need to analyze it and ensure that that represents all possible rectangles, as well as that it's not representing something, as in the case of our 4 points rectangle, it's representing something that isn't a rectangle at all. And so it's our perspective that's valuable. The programming language may just see 5 fields associated with a rectangle object. It says, okay, well, you said there are 5 floats, 5 decimal numbers that are decimal variables that you want me to associate with this larger object that's kind of a container for these 5 fields. We're the ones, though, who get to think of that as a rectangle, or think of a circle as a circle, or think of a much more complicated object as what it is, and then we will need to define what are its crisply defined conceptual boundaries, and make sure that those make sense to other humans as well. So with that kind of grand thought aside, I would ask you to pause and consider what objects we might need for our gravity simulator. What might they need to be called? What fields would they need? And I would ask you to spend a few minutes on this. I'll continue on in the meantime and show you how I had set this up, and how we'll continue thinking about it. So we'll have a universe type. The universe will have 2 fields. One would be a width, so I'm going to assume a square universe, which is just going to allow me to have boundaries. All right, so I won't allow things that kind of go out infinitely far. We're also going to have an array of body objects. That's a field of the universe. So a given universe will have a width to define its boundaries, as well as an array of body objects. And then you say, well, what are the body objects? The objects need to have certain fields as well. We need to name the body, so we need to differentiate Jupiter from Ganymede. And so we need a string that would be the name of the body. We need a float corresponding to the mass that will be valuable when we compute gravity. If we're drawing the body, we probably need to know what color should we color the body, and that might be its own color object. We also need to know the radius. Presumably we're going to draw it as a circle or a sphere if we're in 3 dimensions. And then we need to know, well, what's its current position, what's its current velocity, and at a given point, what's its current acceleration, which corresponds to kind of the direction that that body is being pulled. It may be moving, if you're orbiting a planet, you're moving in one direction while you're getting pulled in a perpendicular direction by the planet. And so each of those I'm going to think of as fields that are their own ordered pairs. So the position of a body is an ordered pair, but also its velocity and acceleration are going to be ordered pairs to say what's my velocity in the one direction or the x direction, and what is it in the y direction. And those x and y values are called components of velocity and acceleration. And I'll say more about that here momentarily. For now, I just want to point out that top-down design has become apparent when you're defining objects here too. It might make sense to think about the universe first, and then once you realize that you're going to need an array of bodies, to think about what fields those bodies will need, and that leads us to an ordered pair object, which we've actually already defined, as well as perhaps a color object when we draw this. And you could add more fields to the bodies, to the body object, but you see the idea that just as when we wrote functions to do something like simulating a cellular automaton, we planned them top down and worked out the details as we went. We're also seeing this kind of top-down design apparent when we plan objects and think about objects as containing other objects as fields. For now, I'll return to our original problem, where we had an initial configuration of the universe, a number of generations, and then this decimal value time corresponding to the length of the interval between time steps. And I want to produce all of the configurations, numgens plus one of them, of the universe, starting with the initial universe, and where every time I'm making an update over an interval given by time. And from our work already, you've become an expert at top-down programming. So if I give you an input and an output, you should be increasingly comfortable with thinking top-down, what's my highest level function, what will solve this problem, and what subroutines will it need? And as I go, what subroutines will they need? And so you might give this a shot. I don't expect you to come up with an entire design in just a few minutes of exactly how this will work on a top-down level, especially because you'll need to know some physics, and I'll get to that very shortly. But you might give a shot at designing this top-down. I'll show you what I have in the meantime. So I have an input and an output here, and my highest level function should reflect that. So I have a time points array that will contain numgens plus one universe objects, and I'm going to set the time points of 0 to that initial universe, and time points is what I will eventually return. And then I need to use, I've used my initial universe parameter, but I need to use numgens and time as well. So I'm going to range over all the number of generations, and I'm going to update based off of time points of I minus 1. I'm going to update time points of I. So I'm going to take the current universe and I'm going to update that into whatever the next universe is. So, and at that next universe will contain all the bodies and their positions and velocities and accelerations after a given amount of time. So I'm going to give the time parameter to update universe as well. And I'll point out that I have a very short function where I've split out the number of generations parameter, and I'll not need to worry about numgens again. So I just need to write an update universe function that takes a given universe as well as the time interval and uses that time interval along with some physics presumably to update that into a new universe. So if I were to plan out that function, update universe, we're now kind of 2 levels down in our function hierarchy. We start with the current universe and we're going to use a time. And so the first thing I might do, analogously to our work with cellular automata, is to create a new universe. So that's going to contain all of the same bodies, but it will have updated positions and velocities and accelerations. And so I might copy over all the information from my current universe into a new universe. And then I'm going to range over that new universe, and I'm going to range over all the bodies that are in it. So in particular, I'm accessing new universe.bodies, which is where those bodies are contained. And I'm going to update the acceleration, the velocity, and the position of that body B as I do that ranging. The order, as you'll see, is important here. I don't want to say more on that currently, but we're going to update the acceleration first. And to do that, I'm going to need to know the positions, and I'm going to have access to all the other bodies because the updated acceleration is going to be related to how I'm getting pulled in all the different possible directions by everything else that's in the universe. Once I have that, it will be actually somewhat quick work to update the velocity and position, as we'll see. But for now, I'm going to point out that it's difficult for me to explain this any further without physics. And so we'll have kind of part 2 of this where we dig into the details of these lower level functions and I work out how is it that I'm going to write this update Excel function that will take a given body and know the statuses of everything else in this universe and use that information to update the acceleration. So where is it that B is getting pulled by all these other bodies? There could be just a few, there could be 100, or there could be thousands. How is it that I'll use that information to update the acceleration of B? And to do that, I'm going to provide a little bit of context in terms of physics if it's been a long time since you've seen this, or if maybe you haven't. One thing I hope you've seen is Newton's third law that says any force has an equal and opposite force. And this will always confuse students. I know it confused me to think that this means that the Earth and the Moon, or the Earth and you, are pulling on each other with the same force. You feel the force of gravity downward towards the center of the Earth, but you're pulling on the Earth with the same force. And the reason how we can kind of get through this conundrum is to look at Newton's second law, make sure we don't skip one, which states that if you have a mass of an object, m, and its acceleration a due to some force, then the value of that force is just F equals m times a, meaning that force and acceleration are inherently tied to each other. If we know the mass, then acceleration is just the product, the byproduct of force. All right. The other thing I would point out to you is that if I divide both sides of that equation and solve for the mass, then the mass is the force over the acceleration, and that will help us understand kind of the quandary of an apple and how an apple and the Earth pull on each other with the same force. So if the apple and the Earth pull on each other with 0.98 newtons, and the apple weighs 0.1 kilograms, then the apple's acceleration towards the center of the Earth as it falls is just the F divided by the mass of the apple. So it's 0.98 newtons over 0.1 kilograms, which is 9.8 meters per second squared. So we see this acceleration where the apple goes faster and faster as it falls. The apple pulls upward on Earth with that same force, but that acceleration is now F over m, but because the mass of the Earth is so much greater, that now when we divide 0.98 newtons divided by this enormous mass of the Earth, the acceleration of the Earth upward towards the apple is negligible. This formula will be very, very helpful for us, because once we understand Newton's second law, we understand that we're going to update the acceleration of a body based off of F divided by m. Okay, so if I know a force, the net force that is acting upon B due to gravity based off of potentially many different bodies, what's the net force that they contribute, then I can simply divide by the mass. And I'm going to be working with x and y components. So if I want to write this update acceleration function and I know what body I'm updating the acceleration of, I need access to everything else in the universe. So I could declare some ordered pair object accel, which has x and y values of 0 when it starts out. I could call a ComputeNetForce function that takes, again, the current universe as well as B, and says, what is the net force acting on B from everything other than B in the universe? And that will give me a force vector or ordered pair. So if you notice in the next two lines, I used force.x and force.y. So I'm going to be thinking about this net force as being an object being pulled in an x direction and being pulled in a y direction. And one of those might be greater than the other. I could be going in either direction in the x direction, or in either direction up or down in the y direction. And if I look at both of those together, that's going to give me a picture of what the net force is acting on B. Then I can simply apply that Newton's second law formula and see that the acceleration in the x direction is just the x component of the force divided by the mass of B, and the acceleration in the y direction is just the y component of that net force divided by the mass of B. So once I write this ComputeNetForce function that takes the universe and the body B and returns the net force exerted by all the bodies in the universe on B, we'll be good to go. I just need a little more physics here to write ComputeNetForce. And so I need to say, well, before I even get to ComputeNetForce, what is the force of gravity? What is the magnitude of the force of gravity that two objects exert on each other? And so if the two objects have masses m1 and m2, and the distance between them is d, then the force of gravity between them is g times the product of the masses over d squared. Here, g is a special gravitational constant, which is 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. And a Newton here is the amount of force that's needed to accelerate an object with a mass of 1 kilogram by 1 meters per second squared. It will allow us to, when we look at the gravitational constant and multiply through, you'll notice that it's meters squared per kilogram squared, and then m1 and m2 are meters squared, and so this will cause, or are in kilograms squared, and so that will cause the kilogram squared term to divide out, and the meters squared term will divide out with the distance as well. And so we'll just be left with newtons after all that cancellation on the right side of this equation. I want to pause though to analyze this equation and notice that what is going to happen to the force, the magnitude of the force here between these two objects due to gravity, if I double one of the masses. So if the mass of m1 doubles, what is it that's going to happen here? Well, we can see that if I double m1, then the right side of that equation is going to double, and so the force will double as well. What would happen if we were suddenly transported to a universe where this gravitational constant g went down by a factor of 100? What would happen then? And here we would see, well, if g went down by a factor of 100, it would be multiplied by 1 over 100, and so the resulting value of f would also decrease by a factor of 100. So f is directly and linearly related to both the gravitational constant g, which is very important, right? Imagine what would happen if g suddenly changed to be 10 times as much. We'd get 10 times heavier, or feel the force of gravity would increase by 10. That might not be good. And the same goes for the masses. So the larger the masses of two objects, the more that gravity will exert a force between them. And the last parameter here is to consider d. So what happens if I triple the distance, for example, between two objects? So d triples. What would happen to f? And so if d went to 3d, then I would get a 9d squared in the bottom. And so I would have something that was 1/9 as big as what I had before. And so f would decrease by a factor of 9. So here you have an even bigger influence of d, where if, say, you double the distance between two objects, the force of gravity goes down by a factor of 4. If they get half as close to each other, the force of gravity increases by a factor of 4. So distance is very, very important. And what it means is that two very distant objects, yourself and a star very far away on the other end of the universe, are not going to have much pull on each other. But gravity is kind of a local force in this regard. So we're looking at bodies that are nearby, and they're going to have much more influence on each other. All right, so now we have that formula. That will become very important soon when we plug it into one of our functions. For now, I'm going to point out we need to know a little about how I'm going to compute a net force. And so I will be able to compute the force of gravity exerted by one body on a given body. But what if I do this for hundreds of bodies? How will I'm getting pulled in all these different directions. How will I sum the contributions of all those forces? So if I have a body A here, for example, and I have a force of 20 newtons up and 30 newtons down, you might pause to consider what the net force acting on this body is. And in this case, 20 of the 20 newtons down will cancel out the 20 newton force up. And so we would have a 10 newton net force straight down. What if I were to make a slight change here and put 30 newton force down and now a 40 newton force to the right? Well, now things get a little trickier. We need to bring in some trigonometry. And I need to realize that, well, if I'm 30 newtons down, I'm going to put the force in the x direction on the head of the 30 newton vector down and find that I'm at this point and that I've formed a right triangle, so I can find the net force, which is the sum of these vectors, is or the magnitude of that net force, I should say, is the hypotenuse of this right triangle. So I can apply the Pythagorean theorem, and I get that 50 is the net force because that's the square root of 30 squared plus 40 squared. The angle there, so to know exactly in which direction I need to head, that angle is going to be given by an inverse tangent. So I need to do a little trigonometry there, but for this specific example, it would be about 36.87 degrees. So if I'm if I'm looking at completely opposite directions, it's just a matter of subtracting the forces. If I'm at right angles to each other, I can handle this with a little bit of trigonometry. But then if we're in two arbitrary directions, then the question becomes, what would we do then? This will still be an addition of vectors. So we're still going to put the tail of one vector onto the head of the other vector. And this will, when we add those two vectors together, we'll see a net force that corresponds to the direction and magnitude of the force resulting from summing the two forces. That doesn't help us immediately see, however, an equation for that net force, which is why we're going to break this down into components. So that will make things much easier for us, as I'm going to show. If I have two forces, say, with magnitude F1 and F2, for example, and I were able to compute if I knew the magnitude of F1, but I also knew its direction, so that's direction, much like with the rotation, can be represented by some angle theta. And I had a different force F2 that also had a direction in some angle from, say, the horizontal alpha. Then I can compute the magnitude of F1 in the x direction and the magnitude of F1 in the y direction by noticing that, well, the cosine of that angle is x1, the adjacent, over the hypotenuse F1. And so I can solve then for x1 by realizing that if cosine of theta is x1 over F1, then x1, the magnitude of that force in the x direction, is just F1 cosine of theta. Similarly, sine of theta is the opposite, which is y1, divided by the magnitude of the force. And so I can solve for y1 and get that y1 is equal to the magnitude F1 times sine of theta. The same goes for any vector. So if I have F2 and alpha, its direction, I can get that x2 is F2 cosine alpha, and y2, the magnitude of the force in the y direction, is F2 sine of alpha. And now it's just a matter of noting that I can view the vectors this way, or I can take the components and first sum x1 and x2, and then sum y1 and y2. And note that the net force will then be x1 plus x2 in the x direction, and y1 plus y2 in the y direction. And now I can easily determine the magnitude of that net force because it's just the Pythagorean theorem again. I could take x1 plus x2 and square them. And they could be in different directions, but then it's just a matter of taking the difference. And I look at y1 plus y2 and square it, and I take the square root of the sum of those two, x1 plus x2 squared and y1 plus y2 squared, and that gives me the magnitude of that net force. Once I have, the key point here is that vectors are easy to add component-wise. If I have them in arbitrary directions, they become difficult to add, but if I break them down into components, then it becomes much more straightforward. If I have a body called A, for example, and it's getting pulled 1 Newton right and 4 Newtons down by one body, and it's getting pulled 5 Newtons right and 2 Newtons up by another body, and it's getting pulled 2 Newtons left and 1 Newton down by a third body, well, the net force acting on it, if I've broken it down into components, is to say, well, it's 1 Newton right and 1 Newton right, 5 Newtons more to the right, so 6 Newtons to the right, and then 2 Newtons to the left, which would give me 4 Newtons to the right. So it's just a matter of adding 1 plus 5 plus, minus 2. The same goes for the y component. So the y components were 4 units down, 2 units up, and 1 unit down. And so minus 4 plus 2 minus 1 gives us a negative 3. So the net force on A can be easily represented in terms of its components, 4 and negative 3. And from that, we could do a little more trigonometry and get the magnitude of the force as well as its direction. But we know it's 4 to the right and 3 down. Okay, so this will allow me to come back to my pseudocode for ComputeNetForce, where I start with an ordered pair object that's going to contain this net force. It will have x component 0 and y component 0 at the start. At the end, that's what I'm going to return, that net force ordered pair. So it's going to say what is the net force's x component, what is its y component, and this is acting on body B by everything in the current universe. So that explains our 2 parameters there. And then the engine for this function is just to range over all the bodies other than B, compute the force that B2 acts on B with, according to the force of gravity. That will give me an ordered pair force, so it will have an x component and a y component, and then add the x component that we find to the net force's x component, add the y component of that force to the net force's y component, and if I do that ranging over every body in the universe other than B, I'll have my net force ordered pair. And so it's just then a matter of writing that compute force function. And so that's now we're kind of one level down in the function hierarchy, where I'm not doing this for many bodies. I'm just saying, what is the force of gravity between B2 and B? And how is it that that's broken into components if I look at the force that's acting on B, according to this gravity between B and B2? So I'm going to again declare an ordered pair object, started at 0, 0. So it's going to have 0 value in the x direction, 0 in the y direction. I now get to apply my force of gravity formula that I had before, where I said, that's better, where I said that F, the magnitude of the force, is equal to our gravitational constant G times the product of the masses. So that's where I can access the fields B dot mass and B2 dot mass. And then I'm going to divide that by the distance between the 2 bodies. And the distance, a distance squared. That distance is a subroutine that I could write. That's just the distance formula that you probably learned in pre-calculus, where we look at the square root of the change in x squared plus the change in y squared between those 2 points. So that gives me the magnitude of that gravitational force. And I want to break that down into its x and y components. So how is it that I can figure that out? Well, I need to figure out the direction that force is being exerted in. So I have a body, B, I have some other body, B2, and I need to determine what that angle is. And I could do a little trigonometry there and determine that angle. And then once I have that angle, remember my formula that if I have a magnitude F, well then the force in the x direction is just going to be that magnitude times cosine of theta, and the magnitude in the y direction, the y component of the force, will be the magnitude F times sine of theta. That will cause our code to get, we'll have a really ugly function angle that requires us to do some inverse trigonometry. Cosine and sine and inverse trig functions will typically be built into a math package for programming languages, but nevertheless it winds up being a little bit ugly, and sometimes the details just have to be, but in this case there will actually be a simpler way for us to write compute force. So we're on the right track. I want to point out that if I've got a body B and a body B2, and I know the distance between them, so ignore the force for a second, but I can compute the distance between them according to the distance formula. And if I know the angle theta, then I get that delta x, kind of the change in x between B and B2, is, this distance is equal to d, the distance between B and B2, times cosine of theta. That's analogous to the formula that we saw before. And the change in the y direction is equal to the magnitude times the sine of that angle. That's great, but actually in the case of 2 bodies, we will be able to easily compute the distance, d, and it will be a little trickier to compute theta, and all we want is cosine and sine of theta. And so note that delta x will be actually quite straightforward to compute. Delta x is just the difference in the x values, which we'll know. If I know b2, I know its position, I know the position of b, so I can just subtract b2.position.x minus b.x, and that will give me delta x. I do the same thing for the y coordinates, and I'll get delta y. So I'll know delta x, delta y, and d quite easily. And so I can then divide then by d, and I get that cosine of theta is just delta x over d, and sine of theta is just delta y over d. And if all I want is cosine and sine of theta, I'll be able to compute them in this way without having to know what theta is. I'll get cosine and sine of theta for free. So that's going to eliminate 3 subroutines here. I'm going to eliminate angle, I'm going to get rid of cosine of theta, and I'm going to get rid of sine of theta. I don't need to call these as subroutines because cosine of theta is just delta x over d, sine of theta is just delta y over d, and it's just a matter of getting delta x and delta y because I already computed d. D is just the distance between the values. I got that subroutine. And remember, f is just g times the product of the masses divided by d squared. And so delta x is, as I mentioned, the difference in the positions, or in the x coordinates of the positions of b2 and b. Delta y is the difference in those y coordinates. And now I can simply apply my formula and say, well, the force in the x direction, how much is b getting pulled in the x direction by b2? It's equal to f times cosine of theta. So it's just f times delta x over d. And the amount that I'm getting pulled by b2 in the y direction is f times delta y over d, since delta y over d was equal to sine of theta. And so I remove those 3 subroutines, and the function just a little bit longer, but this code will be much easier to work with when we implement it in a programming language. I'm going to come back then to update universe and say, well, we started with update acceleration. That meant that we needed to compute a net force, which meant that we needed to determine the force that is exerted between 2 bodies based off of gravity. But once we've done that, we will be able to fill in our update acceleration function. I'm going to assume that we can handle a copy universe function that takes kind of all the fields of one universe and updates them into another. We'll handle that on an implementation level. But we should handle the update velocity and update position functions as well, and then we'll be ready to program. And here's where I'll appeal to physics. So if I can compute the net force that's exerted on an object that's being pulled in potentially many different directions by many different bodies that are different distances to it, and different bodies have different masses, I've already handled that. That's the hard part of the code. I can update the velocity by saying, well, I can just appeal to some equations from dynamics. So if I'm assuming that this acceleration is constant for a period of time, so I have some initial velocity, say I'm a planet, I'm traveling in a certain direction, say perpendicular to Jupiter, and Jupiter is pulling me this way, which means my acceleration will be in this direction. Or maybe it's a little bit in front of me or something, and so I'm going to get pulled in this way. I can break this down into components as well and say that my velocity in an x direction at an updated time point, one way of estimating this would be to say, take whatever I was traveling at the previous time point, and so at time point 0, and add to it the acceleration times the time. Okay, so in other words, if I'm going 1,000 miles per hour or 1,000 kilometers per second, very fast in the x direction, but there's something that's pulling me back, well, if I'm assuming that that pull is constant, the longer the pull happens, the more it's going to decrease my velocity. If I'm getting pushed in that direction, it will increase the velocity the longer that the push happens. And so I'm going to compute that acceleration and multiply it by the time, and then add whatever I started with. And I'm going to do that for the x direction and for the y direction. And so for the position will need to know the current position, and the x component of the current position of the position after time t is going to be the current position. So where did I start? And then it's going to have a contribution from 2 things. Now that I've got the velocity, I can say what's the velocity in the x direction, and after t time, the velocity times the time will be the amount that my position changes according to that. But we also have a term that's 1/2 times the acceleration times the time squared. So if I'm really getting pulled in a direction, that will contribute to that as well, where presumably I'm not only traveling in a current direction, but I'm also getting really pulled aggressively in that direction too, which is going to cause me to my velocity to increase, but also my position to change as well. And so I'll look at that formula in the x direction. I'll look at it with respect to y components as well. Just as with everything else, we'll break down those equations from dynamics in terms of the x component and the y component. And now that we have that, we'll be able to write very short update velocity and update position functions, and we'll be ready to return to the problem of simulating a system of bodies, in particular the moons of Jupiter. And I hope that that will empower you to be ready to extend what we do to an even bigger system, or with many bodies, or extend it to a solar system simulation or a galaxy simulation or this type of thing. So I hope you'll join me for that. That implementation of what we've seen here with our gravity simulation is what we'll focus on next. And until then, thank you for joining me.